Okay, so last week uh, we went about solving boundary value problems, and we saw a few methods, uh, namely like this finite difference shooting methods and all these things. And in the next module, which is the module 11 or the week 11, so we are going to see how can we solve partial differential equations. So till now we haven't seen partial differential equations and their solutions. Like we were dealing with uh, ordinary differential equations. In ordinary differential equations, we were in ordinary differential equations, we were dealing with this. We were dealing with initial value problems and boundary value problems. We saw what can be done to solve these things. Like in initial value problems, we can use explicit, implicit methods. In explicit, like there are RK4, RK5, RK4, like all these kind of different methods are there in implicit methods. Also, there are like different methods. Like in explicit method, there is a solver called OD45, which is a direct MATLAB solver, which we can directly use, or MATLAB function, which we can directly use to solve any initial value problem uh, using OD45. And then in explicit methods, like we can also use this solver called, in implicit method, we use this solver OD15x or OD, also OD23s. So in this implicit method, like like the problem can be solved without depending on the step size. Like no matter how much big you take the step size, like it will be solved. But the uh, computations will be large. Like sometimes there will be nonlinear equations which we have to solve. So uh, it is a bit computationally expensive technique, like to use implicit methods. But this is the only way if you have to solve some stiff uh, like if you have some stiff systems, then OD like implicit methods like or implicit solvers like OD15s or OD23s are a good option to be used. So and then like if your system is not that much stiff, you can use directly OD45, which is very stable. So and then we also have boundary value problems. In boundary value problems, like we can use this shooting method or finite difference method, like whatever different techniques are there, we can use and we can solve our boundary value problem. So in the like uh, in ODs also, like we saw ODs with a single variable, ODs with a uh, uh, ODs in multiple variables. So like both kinds of things we have seen. Now, in this week, we are moving towards partial differential equations. So, in partial differential equations, like we have two or more independent variables. So, for instance, Yeah. So, so the partial differential equations arise when your function has dependence on two or more independent. So these are some of the uh, like things problems which we have solved. So in rod conduction in a steady state, this is a uh, problem which we can solve. When we derive the governing differential equation of it, uh, we will get an ordinary differential equation. And rod conduction in transient state, we will get a partial differential equation in which these variables are like independent variables are t and z. Here only we have one independent variable which is z. Here we have two independent variables which is t comma z. That's why we'll get a partial differential equation. In conduction in a plate, like instead of a rod, like in this, like we will get partial differential equation, but in terms of let's say uh, let's say this is x and this is z. Okay? Partial differential equation x and z. There are two independent variables. So depending upon the problem, you will get some kind of ordinary differential equation or partial differential equation. Uh, depending upon the physics of the problem. So this is a heat loss problem. Like you might have some other chemical reaction or like a vibration problem or something else like a fluid flow problem. So depending upon your problem, you might get some kind of differential equation which governs the physical process of that problem. Like here, the physical process is heat loss. Like you are studying how the heat flows from one end to the other end. So that is the process. Like it could be like how the body is vibrating how the body is vibrating at different points. Like you can have a building how it is vibrating, or you can have a chemical reaction how it is happening in time. Whatever the physical problem you have, you will always end up when you model the physical problem, you will always end up with some kind of this differential equation which might be ordinary or which might be partial in nature. So if you want to get the solution of that problem, like in this case, like you want to know how the heat is flowing from one end to the other end, like then you have to solve the ordinary differential equation uh, to know how what is the temperature at different points on this rod. So you have to solve it. Like in order to solve, we have seen like we have various methods, like all these implicit methods or explicit methods, or like it like depending upon the problem. Like you have if you have a boundary value problem, you have like a different method. So all these things like we have like basically our like whatever there is like our goal is like here in this module our goal is that we have a partial differential equation and we have to solve it to get the solution. So how are we going to solve it? Like uh, which can be used to solve partial differential equations. So like there are basically different kinds of partial differential equation. So this is the general form of second order partial differential equation which you can see. So it like depending upon these values of a, b and c, your partial differential equation can be satisfied as elliptic, parabolic, or hyperbolic. So if this b square minus 4ac is uh, less than zero, it is sorry, I think hyperbolic, right? B square minus 4ac is greater than zero. If b square minus 4ac is greater than zero, then it is hyperbolic. And if b square minus 4ac is equals to zero, then it is a parabolic parabolic PDE. And b square minus 4ac is less than zero, then we call this as a elliptical PDE. So if you want to learn more about this, like you can probably go to the computational techniques course. Like there are a lot of properties of this PDEs. Depending upon that, these names have been derived at. Like if all these are zero, like if A and B and C are zero, and if you have a first order PDE, then that is also called as a hyperbolic PDE because it has some characteristics of hyperbolic PD. So like there is also some theory like why we call the first order PD as a hyperbolic PD. Like you can go and read about it like if you are interested. So this is a Laplace equation. So Laplace equation is this this is nothing but like this is nabla. So you can see this kind of a uh, inverse delta symbol or whatever you want to say, that this symbol is called as nabla. If you don't know, like this, we call it as nabla. Nabla square phi is equals to zero. So this is nothing but like dou square phi by dou x square plus dou square phi by dou y square is equals to zero. So this equation is denoting it. So this equation is denoting this. So nabla square is nothing but this dou square y by dou x square plus dou square y by dou x square. So we know, like if you know divergence, uh, you know gradient, you might be knowing like del is equals to I into dou by dou x plus j into dou by dou y. So if you do dot product of del dot del, then you'll get this del square. So that's why you get dou square uh, by dou x square plus dou square by dou y square. So here you can see A and C are basically 1 and B is 0. So that's why uh, you will get this B square minus 4AC less than 0. So that's why this is a elliptic QT. And this is nothing but UTT is nothing but u dou square U by dou T square. So this symbol denotes that like second order differentiation of U in T is equals to C square into rho square U by rho x square. So this is a wave equation, 1D wave equation. So like let's say if you have some rod and if you apply some kind of impact force at this, how uh, the impact is propagating through it, like this will be given by this 1D wave equation. So like if you apply a very like force at a short period of time, like if you just like take like if you just have like take somebody and if you just hit it, like if somebody hits it, like you will feel like some wave is traveling to your body. No? So that kind of phenomena is given by this wave equation. And this is heat equation, which is given by dou P by dou T plus alpha into again this del square x square phi plus del square phi by del y square. So this again, let's check how we can get this parabolic and uh, hyperbolic things. So because this I don't, parabolic, uh, okay. So these are different examples of equations which we get in uh, partial differential equations which we get in like different fields uh, heat transfer, mechanical engineering, which is in mechanical systems, wave equation, heat equation, Poisson equation. Like depending upon your area of interest, like you might end up with these kind of equations. Your phenomena might be different, but you will always have these kind of equations. Uh, like instead of this U, you might have something else like chemical reaction rate or something. So So physical process doesn't matter here. Like the kind of equations matter. Like every equation is a partial differential equation, and we want to solve it. And each partial differential equation, and we classify it as elliptical, hyperbolic, or parabolic, depending upon the this classification which we have explained. Yeah. So this is the introduction to partial differential equations, which we have seen in the first lecture of this module. And then we moved on to how we can solve these partial differential equations to get the solution. So,
Excuse me,
yeah,
sir.
yeah, yeah,
Sir,
that's,
can you just go to the previous slide where you have got
yeah,
all PDEs? Here.
yeah,
Uh,
mm,
Coming to wave equation, we have second derivative of time. Heat equation, we have
yeah,
first derivative of time.
yeah,
Now coming to wave equation, it is having one special term, that is x. So when we are talking about classification of PDEs, now what the
mm,
concept is, it was two dimension. So
mm,
when we are talking about the classification of PDE, so time also will be taken in something like special the term, special term.
yeah, 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 yeah.
Okay, and
Here, here,
yeah,
XY is not necessarily XY. It can be XT, XZ. It can be
so
anything.
it can be time also. It can be time also.
Yeah, yeah, yeah.
Okay,
It can be time also.
okay, sir. Thank you.
Yeah. Like XY are independent variables. It can be spatial coordinate. It can be spatial variables, or it can be temporal variables like time, whatever it.
Okay, so then in this, I don't know how well this question can be posed. Just I had a curiosity about this. So now,
Yeah.
actually, one of some long back, I just gone through some video where it was three dimensions. So they were
Mm.
taking the eigenvalue, and from eigenvalue, whether if eigenvalue repeated, non-repeated, as per that they were classifying different
Yeah, yeah,
PDEs, parabolic,
yeah,
elliptic, and this one. Now there, when they
yeah,
were
yeah.
discussing, it was a three coordinate system XYZ. Now my doubt
Mm.
is, let us suppose I will bring time also into consideration. For example, hyperbolic, second derivative time
Mm.
will be there. So can
Mm.
you just put some light on how can we classify if we have got three dimension, that is XYZ, spatial coordinate, and we have
Mm.
time also. Do we have any such concept where we can think of classifying?
Yeah, I think you can classify it. I have no idea. This is what I
But
have learned. But I think yeah, you will
but
have
the concept may
like
exist.
mm,
But concept may exist. I think that still we are not
yeah,
familiar,
yeah,
but I think concept may exist. No.
yeah, yeah. It will
Okay.
exist. It will exist.
Okay, sir. Fine. Thank
I'll
you.
just check and let you know.
Yeah,
Uh,
please. Thank you, sir.
Three-dimensional.
With the unsteady, because as soon we said time is there, it is unsteady
Hmm,
flow. Because even no,
three-dimensional PD in space. Yeah.
yeah, actually I did viscoelastic, and viscoelastic fluid will come into picture only in unsteady flow. As soon as it is steady flow, the viscoelastic flow effect will just vanish, and it will be a Newtonian fluid.
Okay.
So that time we were not much about this category, this classification. So
Hmm.
that's what I just flashed. Thank you, sir. I will be waiting for your answer next class. Thank you.
No, no. Just checking. I'll just see.
Oh, no. Okay, okay.
Four independent variables. Hmm. Okay. Okay. So they are saying that let's say if you have if you have a PD in four variables, like let's say x, y, z, and t, and let's say if you can write that as a into dou square u by dou x square plus b into dou square u by dou y square plus b into dou square u by dou z square plus t into dou square u by dou t square. So then you will write this coefficient matrix M as A 0 0 0 0 B 0 0 0 0 C 0 0 0 D. And you will find out the eigenvalues of this matrix. Uh, if all the values are like positive, like here the this is the diagonal matrix, so the diagonal elements will be the eigenvalues. So if these are positive, then this is a if these are all are positive or if these all are negative, then this is a elliptic.
Okay.
Yeah. So here and also like here there are zeros. Like if you have like let's say if you have some term like in this equation there are like no terms. Like if you have some term like dou x by dou y, then you can include it here. Like you can write it. Like if there is some coefficient which is let's say e, then you can write it like here. So here there are no such terms, so that's why I'm keeping it as zero here. So then you find out the eigenvalues of the matrix, this coefficient matrix, And if these are like all positive or if all negative, then this is the elliptic system. And if one is zero, if one eigenvalue is zero, then that is a parabolic system. If any one eigenvalue is zero, then that is a parabolic system. If one is zero and all others have same sign, then we have for hyperbolic. If one eigenvalue has a different sign than others, one eigenvalue has a different sign than others, then that is a hyperbolic system. Hyperbolic. So if if you have like uh, uh, two positive and two negative, then that is ultra hyperbolic. I don't know what it is. Ultra hyperbolic. So this is the classification. I think like this formula which we got here, b square minus 4ac, this can also be derived by this, I think. So this
Okay,
like
sir.
using
Thank you.
this eigenvalues concept, like you can derive this formula, like b square minus 4ac. That can also be derived using this. So this is the classification how we can do. So you can do this for any kind of like any number of independent variables. Uh, like you can do this for like here 4 we have taken, like if you can take some 10 or something, like you can do this class. The PD So this classification is only for second order PDs. I don't think this exists for higher order PDs like third order or fourth order. Yeah. Let me just see.
Yeah, I think even sir, geometrically meaning also, I think maximum is second or third order derivative. I think so. Even physical
Ah,
interpretation. I mean, I think
ah.
beyond that, there is no such physical interpretation.
Hmm. No, there
That's what
might
I
you might have some cases. You might have in some cases
making
uh,
like
in beam problem in mechanical engineering or civil engineering, we have a beam problem. So
what is the highest
like
derivative, sir? That
huh? Hmm?
what is the highest derivative in that beam problem?
We can get
You
up
are,
to fourth order like fourth order
okay.
PD. So
Because yeah, okay. Because once
mm,
jerk is jerk,
yeah, yeah,
sudden rate of change of
yeah,
acceleration.
yeah,
That's a third order. Till there, I have
yeah,
yeah.
yeah.
Yes, okay.
So
So in beam,
you can have higher order PDs, but this classification doesn't apply to this. Like
okay. So fourth order is
hyperbolic,
in beam, no?
yeah,
Sir,
fourth
fourth
order
order
is
in beam.
yeah, yeah. You can get fourth order PD for a beam. Uh,
Okay, thank you,
uh,
sir.
beam question. Yeah, so like classification, these kinds of classification, this is only for uh, second order PDs. So like here we are uh, uh, like doing this like coding using this uh, the approaches we will learn today. But like these problems partial differential equations can also be solved using like there are various softwares like If you are like working in the field of mechanical engineering, like fluid mechanics or solid mechanics, like you can use this software called Abacus, ANSYS, like fluid flow, uh, ANSYS, and there is also software called OpenFlow, like, and also there is a software called COMSOL, like, so different, like depending upon the application, like you can use like different uh, commercial softwares solvers which we can use. Like you have to buy these softwares. Like we don't have to write codes. Like you have to just give the geometry and boundary conditions. Uh, Depending upon that, like entire process of the code running will be in the background. Like you will have a nice graphical interface, and then after solving it will give the results like nicely in a very presentable manner. So like like this PDs can also be like solved like uh, like there are different techniques called finite difference we saw already like in the 10th week, like how we can solve boundary value problems using this finite difference scheme. Like there is also something called finite volume method. Like this you can use mainly in case of not solid mechanics, like in case of fluid mechanics problems. Finite element like is like the most common method which we use in solid mechanics. So and like there is also like combination of finite element, finite difference, finite volume called computational fluid dynamics, like which we use for fluid dynamics problems. So these kind of approaches are being followed by these commercial solvers. So if you are someone working in like fluid mechanics or like mechanical engineering, or like I think there is also there will be also some kind of commercial softwares like this for I think electrical engineering also. Like it comes so like you can solve also this multi-physics problems, like uh, coupling of mechanical and electrical uh, systems. Like you have a piezoelectric material on which if you apply stress, there is a generation of potential, and like there is like you can also solve electrical and heat related problems which are coupled, like different things you can do with console. So but here we will manually code, and like we will see how can we solve our PD. So so there are uh, like as we see, like there are lot of problems which we can solve, like elliptic, parabolic, hyperbolic. So these are like a very broad range of problems, and like we cannot say one solution, like we cannot say one approach will fit everything. Like as I've said, like you cannot use finite element probably for fluid mechanics problem. So you have to use finite volume or some different kind of method. So for each kind of a PD which you have, like you have to use the approach which suits it better. Like if your system is elliptic or parabolic, depending upon it, you have to use some kind of approach that will give you good solutions. Otherwise, numerical solutions are like always approximate. And if you don't use a particular, like if you don't use a proper method, like you will get some solution, but that solution won't be correct. You will end up you will end up with some random solution which doesn't have any meaning. So we have to be very careful when we go for these numerical techniques, and we have to use methods according to the problem which we have at hand. So I think yeah. So here uh, first we will see this problem uh, we will use this method called method of lines. So let's say you have this kind of problem. Like this is a heat conduction problem. So in which we have a rod on one end of it. We have 100 degrees Celsius, and on the other end, the temperature of the rod is 25 degrees Celsius. So, like from here to here, as like heat flows from higher temperature to the lower temperature, there is heat loss, and by the end, like it will be 25 degrees Celsius. Like so, initially at t is equals to 0, like this is a uh, transient problem. Like earlier we had solved this the same problem, but when this dou t by uh, like uh, dou t by dou t, which is the dou capital T by dou small t, is 0. Like earlier we had solved this same problem for in the last week we have solved this same problem for this steady state, but this is a transient state problem. So it means that as temperature varies, the as time is varying, the temperature is also varying at various points in the peak. Like we will see how we can solve it. So, but one thing is constant here, that at all times, the boundaries have this, regardless of the time, we have these boundaries constant, having constant temperature. So, like, if you take temperature as a function of z is nothing but this direction. Like z is 0 to and z is equals to L, like at the end. So t z comma t, we can write this as t z comma t because we have two independent. So at z is equals to 0 at all times, we have temperature is 100, and at z is equals to 1 at all times, we have this temperature is 25 degrees Celsius. And also, this is our initial condition that at all points on the at all points, like we are at all points, we are taking uh, like except at the first point, except at this left hand, at everywhere we are considering temperature as 25 degrees Celsius initially, and then after some time, like this 25 will like as time increases, like this 25 will vary. Like we will see how we can solve it. So we will use heat transfer. Sorry, this a method of lines to solve this problem. We will see how uh, we can use it. So let's look at it. Like so, what we will do is like we have a we have a rod like this. Now we will divide the spatial domain into some n segments, like one, two, and like some n segments. And each segment will have some length, which is L by n. So each segment will have some length, which is L by n. Or let's say this, you can also call it as delta x. And we will use the uh, this central difference formula to get this second order differentiation of t with respect to x. Like this, we have already done in the boundary value problem. Uh, last week, we have seen this is the central difference formula. Yeah. So we have like lot of points, or like one, like if you have n segments, you will have n plus one points. Like at n plus one points, we have to uh, at n plus one. So these are the element numbers, these are the segment numbers, and these are the boundary. points. Okay, so circle in circle. I'm writing in circle because I want to differentiate them as boundary points. So like up to n plus one, we will have this. Okay, so we want to find out what is the temperature at T at point two, at point three, at point four, at point n plus one with at various times, like as time varies. How is the temperature at point two varying? How is the temperature at point three varying? How is the temperature at point four varying? Okay. Earlier we had the steady state problem. So in steady state problem, this temperature at point two, at point three, and at point four will be constant because it has reached steady state. There won't be any variation with time. But because this is a transient state problem, here the temperature at each point will be varying with respect to time. Like after some certain point of time, it will reach a constant temperature. We will see like if it reaches a constant temperature, then we will say that this is like the rod has reached the steady state. Okay, so we will get the solution by using this. Like we will discretize the domain by using this uh, finite difference scheme, and we will get we will use the central difference formula to get various like the differentiation of second order differentiation of uh, t with respect to it. So now like for each point like you can start from here, you can start dou square t by dou x square uh, at 2 is equals to dou square dou 3 minus dou 2t2 minus 2t1 by like h square. Like then you can go to the third point. Third point, the second order differentiation temperature will be, we'll have T4 minus 2, 3, 2 and minus 2, T2 by H square. So like this, we go on doing this up to nth point. So we go on doing this up to the nth point. So at the end point, you will have Tn plus 1 minus 2 Tn minus 2 minus 1 by H square. Okay. So then you will have then you will replace dou square t by dou t square in this equation. So you will get at each point you will get this dou t by dou t I is equals to ti plus 1 minus ti by ti minus 1 by h square plus minus beta into t minus sorry here because I am taking at ith point, so ti minus t. So for each point from I is equals to sorry I is equals to sorry this is 2 to n plus yeah n only. So you will have this number of equations like from first to uh, from I is equals to 1 to I is equals to n plus 1, you will have uh, n plus 1 equations. In that like di this dt by uh, dt at I is equals to 1 will be 0 and n plus 1 will be 0. So we don't take like we know already. So we don't take those values, and then like uh, we will have some n 2 to n equations. So we will take all these equations and we will solve them. So we will solve all the equations from uh, which are like dt. dt by dt2 is equals to something, dt by dt3 is equals to something up to n. Like you will have n equations and you will solve all of them at once. So these are all ordinary differential equations. Earlier also we have seen we have solved like when like we converted a second order equation, like if we had something like this dou square y by dou t square, we converted this into a uh, ordinary differential equation of higher order into like two equations of single order, and we have solved this problem. So like this is the same thing. Like there we had solved the two differential order differential equation at once. Now we are solving n order like n ordinary differential equations at once. So that's how we discretize the domain and convert this ordinary differential equation into a partial differential equation into an ordinary differential equation. And we like we had one partial differential equation and now it is converted into some n ordinary differential equations. So now we have to solve n ordinary differential equations to get our solution. So we will see how have we done this in MATLAB, the solution of it. So first of all, I will write a function to get this n ordinary differential equations. So this function will give me this like all the ordinary differential equations from 2 to n, and then I will uh, solve this ordinary differential equations in another script. So this is the script which we will solve. Like we are using OD45 to solve this n ordinary differential equations. Okay, so this is the function. So like we know TA is 25, which is given. Alpha and beta are things which are given. So and then we have so y is nothing but all that y is a vector which has all the values of temperature at all nodes uh, from the second node to the last but one node. So y has all these values of temperature. So or if I want to calculate number of uh, segments, like then I can get like uh, I can do this like length of y plus 1 will get like number of divisions I have made in the bar. So and T of 1, which is like we know like at all temperatures at the left end the temperature is 100, we know this. And from T2 to n we are saying that that is y, like we don't know, we have to solve this, like we have to solve for y. And at the last node, which is the n plus 1th node of the bar, we have TA, which is the temperature is equals to 25. So h is equals to 1 by n. So uh, like n is nothing but number of divisions. Like here this 1 is the length of the bar. Like here the length of the bar is 1 meter. So that's why I have written 1. Like you can also write like this. to avoid confusion, like if you want to change it in the future, uh, this value, this is alpha. So now I have n plus one nodes, right? For each node, I want dt by dt. So I will initialize with a zero row vector, which is zero column vector. So initially I'll initialize it. So zeros of n plus one comma one. So for 2 to n, we have seen that we can discretize using the central difference scheme, and we will get this form. And then we will extract uh, dt by dt from second node to the last but one node. So we will have this all this like this function will give me all the differential equations from uh, for differentiation of temperature with respect to time from the second node to the last but one node. Uh, and then I will solve it like I have like I'm giving n is equals to 10 here, like and then I have to initialize the temperature, right? So like I have to give the initial values because I have converted this into a ODE. So this ODE is like now an initial value problem. So all these ODEs are converted into an initial value problem because they are with respect to time. So I have to give the initial values for temperature at all nodes. So at the first node, the temperature is 100, and at all the other nodes, the temperature is 25 because it is given in the problem. Like here we have seen, right? Like where is it? Yeah. Uh, think so. Yeah. Initially, the entire rod is uniformly at 25 degrees Celsius. So that's why we are initializing it. Like we are saying that initial temperature at all the other nodes except the first node is 25 degrees Celsius. And I want to solve the PDs, like all the ODEs, like which are with respect to time, to get the solution, which is nothing but the temperature here. Like how I want to know how temperature is varying with respect to time at various points on this rod. So I want to solve. So like I will solve it for 20 seconds, like 0 to 20. This is the time span which I am taking. Like you can take for 10 seconds or 20 seconds or 100 seconds, like depending upon you want, you can take it. And then you have to give the initial condition, right? Like y naught is equals to, so this is the uh, initial condition which we have to give. So the temperature at T 2 to n is uh, initially 25 degrees that we are giving here in the in the OD45 solver as the initial condition. So that is why not. And you have 2 to n this rod conduct t comma y function will give all the ordinary differential equations from 2 to n. So dt by dt from 2 to n. So and then if you solve it, you will get the result. Like we will see how we are getting the solution. I'll run it. So now you can see this is my plot. So the temperature at various points is varying like this. So initially, everything was 25 degrees Celsius, and but like after time passes, like this is the temperature at the this is the temperature at the second node, and this is the temperature at the uh, last last but one node. So last but one node, like it reaches a steady state at 29.1. So now you can see that like everything is converging. Like after some point of time, everything is becoming a constant. When everything like this becomes a constant in time, like with respect to time, then we can say that system has reached the steady state. So if things are like if the temperature is becoming constant after certain point of time, like then we can say that like the system has attained the steady state. So here that is what happening. So after certain point of time, temperature doesn't change with respect to time. So then we can say like dou T by dou T is equals to 0. So that's why we say like if you are like calculating beyond this, you can simply take dou T by dou T is equals to 0 and solve your problem. Then you will get the steady state solution. So that is the difference between steady state solution and the transient state solution. So transient state solution is like when we want to calculate when temperature is when something is varying with respect to time. So that's what the difference is. So that's how we have solved this rod conduction problem, which is a second order uh, partial differential equation to get the solution of temperature varying with respect to time at various points on the rod. So here we have used the method of lines. Okay.
Can you kindly go to the code one, sir?
Yeah. Uh, yeah.
Sir, calling function, can you get
Yeah.
calling function?
Calling function. This one.
Yes. So in line number 9,
Hmm.
I have a doubt in line number 9. Why it is length of y plus 1?
Length of y plus 1. Why is it length of y plus 1? Because we are saying that y is a vector which has temperature from second node to the last but one node, right?
Second is the last one. But n minus 1. No?
No, no, n minus n plus 1 doesn't come up to n, up to n. So last node is n plus 1, first node is
Okay.
1.
So now
So
y has what from?
this y
Minus
has
2.
this y is a vector from t2 to tn. It doesn't
Okay.
have t1 and tn plus 1.
Okay.
So now if you if you add plus 1, if you add plus 1 to it, then it will give number of segments, right? Like basically if you have n plus 1 nodes, you will have n segments,
Yes. Okay.
right? Right.
So now, yes, sir. Yes, sir. Right.
uh, yeah,
So this n sums the number of segments.
yeah, this n is nothing but the number of segments, number of
Okay. Number of
segments.
intervals.
uh,
Okay. Number of intervals. So if I say from 2 to n, right? No. So
yeah,
2
yeah.
to n. So
Mm,
so I want to talk regarding number of intervals. So
mm.
we are writing plus 1. So this plus 1 is neither including node point at 1 nor is including node at n plus 1. Am I right?
No, no, this is just adding, like this is a little bit like, okay, this I think
No,
is making things difficult. You can just uh, I'll just tell. Okay. Okay.
what my doubt is
Hmm.
whether a plus 1 is adding any of the node points like
No,
n
no, no,
plus
it is
1.
not adding. It is not adding. I'll
Okay.
just show you. This. Uh, let's say you have, so this is your rod, okay? Uh,
Okay.
and I'll take this. So I'll divide it like this. Two, three, four, five, something like this. So this is 1, okay? And this is n plus 1, okay? This is node 1, and this is node n plus 1. And this is n. So this Y will have all the temperatures from here to here. Y will have all temperatures from T2 to Tn. It doesn't include T1 and Tn plus 1. Okay.
Okay.
So like if you have n plus 1 nodes, if you have n plus 1 nodes, then the number of segments which you can like if let's say if you
We'll
have
have less segments. So 1 plus 1 nodes will be having 1 nodes.
if you have two
Sorry,
segments
1
like
segments.
this, if you have two segments, then you will have three nodes, right?
Okay.
Sorry,
Huh?
sorry. I'll
Okay.
just if you have like this is one segment and this is second segment, then you will have three nodes,
Yes.
right?
Yes, sir.
Hmm. So now if you have only this, then how can you find out the number of segments? You add plus one, right? So like if you have only internal node two, right? Like this is like this y has only internal node, right? So we are not taking one and three. So length of this vector will be one, right? So if I want to get the number of segments, I'll add just plus one.
Oh, okay.
Hmm.
Take a pic.
Yeah, this
Correct.
is just making life complicated, but yeah. Okay.
Yes, sir. Clear, sir. Thank you. I have taken a pic. Thank you.
Okay. We can just write it as like 10. Like, it doesn't matter, but yeah. Because we have already given ns time. So I've just copied the code, written the code as it was done in class. So the confusion. Okay, so I think yeah, we will see same kind of problem if we have. Uh, so, so this is also a transient state problem. Mm. And we have to solve it using okay, yes. Okay, sorry, we have to solve. We will solve the practice assignment. Should not solve the assignment problem. So this is same kind of problem. We have to solve uh, this problem using this equation which is given. So D is some parameter, K is some parameter, and capital K is some parameter. We have to solve for C. So the initial condition here is I'll just take my code which we have written. Uh, what I'll do is I'll just take this code and I'll modify it. Repeat exam. I'll write this function in the then. Let's keep the name as it is. Now let's modify this code. So here mm, at these are the initial conditions which we have given. So here this is like we will change it to instead of uh, this and write like it's a CA here. And this is not alpha. Like here we have D, capital D is equal to 0.01 and small k is equals to 0.2, capital K is equals to 0. And here we will use C instead of C because this is concentration. So at the end, the concentration is Ca and this is 0 because it is given. And at the first point, the concentration is 1. And at the end, the concentration is 0. And we have what is Z? Yeah, Z is also is equals to 1. Length of the length here is also is equals to 1. And we want to uh, and then we will define this equation here. So instead of this, we will use the our our central difference scheme. Here we will use C instead of T. Entire thing is same. And here instead of this, we will have K plus K into C of I divided by K plus capital K plus C of I. So, so that is the equation here which we have. I think, yeah. Okay. So the function is modified. We will write it as DCDT instead of DTDC. The function is modified, and now I have to solve it. So, so the number of divisions they have asked here also they have taken 10 intervals. So n is 10 itself. And, here this is 1. And and they are saying that C is 0 for all initial value of C is taken as 0. So I'm taking it as 0. And this also should be 0. And then we will solve this. Uh, so they have asked about only like, they have asked everything uh, for time t is equals to 2. So t is equals to 2. So I will solve up to only 2 seconds. And these are my initial conditions again. Okay. Let's solve this. I have to include this. I have to write down in the end of the function. I have changed the problem accordingly, like the same code we have used. So, so this is the like uh, this is the plot which I am getting. Like each plot is for a particular each plot is for a particular location. So this is varying with respect to time. So each plot is for uh, this is for at sorry, at z is equals to 0.1, and this is for at z is equals to 0.2. So at z is equals to 0.2, at t is equals to the concentration here is what is the value which we are getting at the end point, which is 1.98. 0. Mm, or we will just look at this. So we are getting y solve. So y solve is uh, y solve has all the values. So you can see this uh, this uh, the first column has variation of concentration at z is equals to 2, variation of c at z is equals to 2 with respect to time. So it is going on up to like 2 seconds, and at the end of 2 seconds this is the value. So so at 0.1 this is the value, at 0.2 at z is equals to 0.2 this is my at the end of 2 seconds this is the concentration which I'm getting, 0.4038, and at location 0.4 this is the value which should be 0.080, and at location 0.6 this is the value which will get 0.0084, and this is the value which will get at 0.2 0.8, which is 0.000513, something like this. Let's check. Let's submit and check the answer. Yeah, we are getting some kind of error. Uh, 0.6. Oh yeah, this is 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0. Okay. Well, different. Here's the MATLAB. What we have done is right. I don't know. Right. We check our code. This is fine. B 0.01. A is 0.2. A is equals to, okay, this is fine. This is fine. This is fine. This is fine. At the end, yeah, is equals to n m. And we have two that yeah, one square into two, yeah, that is fine. A into 3 5 and A plus A. Okay, this is also fine. The first point we have this and okay, 0 to 2. So, uh, 1 second. I don't know. I think what we have done is correct. Maybe these answers are not right here. What they have given here, we will just move on. So what we have done is exactly right. There is no confusion regarding that. Just check again. Till then, uh, we'll move to the next part of the module, which, which was solving these hyperbolic PDEs, which are first order. Here we are going for the first order PD is using our method of lines. So here we will discretize the system uh, like this is a first order differential equation with respect to z, partial differential equation with respect to the z. We can use the central difference scheme and solve it like what we have done, like the same thing we can do. Uh, like the initial conditions are given, and also the boundary conditions are given. So like if if I if I uh, if I use the central difference scheme for the first order partial differential equation, so we saw in the lecture that this was not giving correct solutions. Like there was some numerical problems. So we won't use the central difference scheme for discretizing the domain. So here instead of using central difference scheme, we will use the backward difference formula. So that is dou theta by dou z at I is equals to theta I minus theta I minus 1 by uh, delta x. So or delta z. So we will go for the second central difference. So sorry, the backward difference formula will be used instead of using the standard central difference scheme for first order PDs. So we have this code. So this is using the first using the backward difference uh, formula. This is not central difference. So, we are dividing this domain into 50 segments. Like earlier, for the conduction problem, we have divided it into 10. Like here, we are dividing it into 50 segments. So, and like this is the function which will be giving, which gives me all the ordinary differential equations from the uh, first point to the last point. So here uh, here we have the um, boundary values. Like we have two boundary values because this is a second order differential equation, right? Like we should have two boundary values, but here we will have only one boundary condition. So which is at z is equals to 0. At z is equals to 1, we don't have. We have to solve for z is equals to 1. So that's why we don't have. So that's why we go from 2 to end. So earlier we went only from 2 to n, right? So here we will go from 2 to n plus 1. So that's the difference here. So these are all the parameters which we have, like u is equals to 0. So here this parameter u is equals to 0.5, k is equals to 1, and all these things. Like then we have uh, theta. So theta is a vector like which has all the values of theta from first end to the last, uh, first node to the last node. So first node is already given, which is the boundary condition. So that's why this is we are giving it as theta n, and y is the solution from the second node to the last node for values of theta. So y is something which we have to solve for. So y is the value uh, we solve for the values of y. And then we have d theta. So d theta by dt. So this is d theta by dt, or like we can, I'm just writing it as d theta. So we will initialize it with a zero vector because we have n segments and n plus 1 nodes. So we will initialize this like this. And from I is equals to 2 to n, or I is equals to 2 to n plus 1, like I will just write it. So this is my uh, formula. So d theta by dt is equals to minus u into theta I minus 1 by h. minus k into theta I. So, and I have to write one more. So, so like I'm using backward difference formula from going towards like from going from like for going from the second node to the last node to get the value of our ordinary differential. And then I will get all those ordinary differential equations as the output of this function. And after getting all the ordinary differential equations from the output of this function, I will have to solve this ordinary differential equation. So again, we will use the OD45 to solve our ordinary differential equations. So PFR function y will give all the values of ordinary differential equation, like all the ordinary differential equations will be given by this PFR function. And then I have like I am solving it like for different points of time. Like earlier we were solving it for 0 to 20. Here I want to solve it only for these points like 0 to 5, but at these specific points. So I am giving that time span. And then I will also have to give what is the initial value of theta uh, from the second node to the last node. This y naught will have the initial value of theta. At t is equals to 0, what will be the value of theta from the second node to the last node? This y naught will include that. So it is given that theta naught is equals to 0. So at initially all the values of theta are 0. So that's why y naught is equals to, we are giving zeros of n comma 1. So we are remove like we are not taking the initial point here. So initial point, because the boundary condition is already given, which is theta is equals to 1. And then we will solve it. So after solving it, we will get uh, t solve and y solve. Like if you want to like plot uh, like instead of this, I can also like let's say I can plot h2 h of h, sorry, t solve uh, t solve y solve. So just run it. I'll include these lines PLC because I don't want the other code to interfere this code. So I'll remove all the variables, all the and close all the plots which I have already plotted. Otherwise, they will overlap. So, so this is how it is looking like. We have like 50 nodes, right? So for all the 50 nodes, this is how our plot looks like. So this plot has 50 plots. So this figure has 50 plots for each 51. Sorry, it has yeah 51, not 51. We have taken 50 segments, right? Yeah. So it will have except for the first point, it will have 50 plots. So this is how with respect to the time at various points on the rod uh, or rod or something like va- various points in the space domain, uh, theta is varying with respect to the time. So I just want to plot mm, instead of this. I am just interested to plot uh, this plot, which is a plot for various like at all the intervals like I want to take the x-axis as the uh, instead of time I want to take x-axis as my uh, uh, space domain or like length of the rod. So I want to see how with respect to the length of the rod at these times theta is varying. So I can run and I can see that this is how it is varying. So this each plot is for a single time, and this is how theta is varying for uh, uh, theta is varying with respect to the length of the rod. So at this is at initial this is at the uh, I think at t is equals to 5, this is the plot, and at t is equals to 1, this is the plot, and at t is equals to 0.5, this is the plot, and t is equals to 0, this is the plot. So this is how my uh, theta is varying with respect to the length of the rod for different points in time. So earlier, if we used central difference scheme, this was going beyond this. So that is not technically possible. Uh, that is not a practical scenario. Like this plot should not go beyond this. Okay. So this is our steady state. This this plot should not, like the second plot should not go beyond the steady state. So that is not a practically possible scenario. So that's what instead of, that's why we are using the backward difference formula instead of the central difference scheme here. Okay. We have a similar kind of problem we will see, but I'll just check the last problem what we have done. This problem what we run. I have just asked ChatGPT to write the code. Let's see if it will give correct answer. Like we got what we were getting earlier only. So our code is correct. I think these answers are wrong. What we have written is right. Yeah. Okay, we will see the this. I think this question is also wrong. Uh, so we won't solve this. Uh, this is not a first order PD. This is a second order. I think there is some mistake in this question. Practice problem. And we'll go to the third problem in the practice assignment, uh, which has this heat conduction with a Newman boundary condition. So in the tenth assignment, we used the ghost point method. So instead of like we uh, we will now consider a transient version of the same problem. So so this is my parabolic PD, and here uh, instead of the boundary condition. Uh, like earlier we got earlier we had temperature at T is equals to 0. Sorry, at T is equals to at Z is equals to 0 was 100, and at Z is equals to L the temperature was given as 25. instead of the temperature, here we are getting dou T by dou Z at Z is equals to L as 0. So this is a Neumann boundary condition. So, and this is a Dirichlet boundary condition. So we have two boundary condition, and though both are different, like earlier we had Dirichlet boundary condition. So we have to solve this. So, and like somehow get the result. Like, so what we can do is like the same procedure we will follow, like what we have done. We will just take the same procedure, like I can just copy this code and we will make some changes according to the condition of the problem. Yeah. So this is the rod conduction problem itself. Uh, or okay, I'll do this. I'll copy this. Okay, and I'll copy this function also. And, I'll save this as example two. So now we have initial condition. Initial condition is 25 degrees. So that is fine. Like here also the initial condition at all points uh, from 0 to Z to L. So for the entire length, so initial condition is 25. Okay. So then we have to like uh, we have to solve here for t is equals to like 2 seconds only. So I'll just solve from t to instead of 20, I'll go from t to 0 to 2 seconds. And here, because this is not something which I have got, so like TA is not known here. So TA is not given, so I'll remove this. Okay. So at the end point, what is the temperature? I don't know. I'll remove it, and I will apply the central difference scheme from mm, from 2 to n. Okay, from 2 to n, I'll apply the central difference scheme. Where I now I also have to apply the central difference scheme for n plus 1 also. So at point n plus 1 also I have to apply it. So if I apply the central difference scheme, like here k bar, yeah, somebody is asking a question. You want to ask? Okay. So here k bar is nothing but alpha and beta is nothing but h bar. Okay. Whatever we have here, h and beta. Okay. I'll just change this values. K bar is 0.05. Okay, and beta is 0.2. And this is positive beta here. So h bar is positive, so I am writing positive. And instead of TA, I'll write this as 25. Yes. Now I have this same thing. I'll just copy paste this. So now you can see that I have to go from like if I take the central difference scheme at point n plus 1, I will get this term Tn plus. So Tn plus 2 is something which is like beyond, like I'm going beyond the road. So this is not a practical thing to do. So what I'll do is I'll take this condition. I'll take this condition, which is dou t by dou z at uh, at n plus 1 is equals to 0, right? So I'll apply the backward difference formula like at the end. So I'll apply like dou t by dou z at n plus 1 is equals to t n plus uh, t n plus 2 minus tn. Sorry, I'll apply the central difference scheme at the end point, which is tn plus 2 minus tn by 2h is equals to 0. So then this will then this condition will make tn plus 1 tn plus 2 minus tn is equals to 0. So that gives me tn plus 2 minus tn is equals to 0. So I can replace this ghost point, which is going like something which is like beyond going the rod dimension of the rod. So there is no point like beyond tn plus 1. So I can replace this with tn here. So I'll replace this with tn and my problem is solved. So I have to solve this from 2 to n plus 1. I have to do this. So, so I have to solve all the equations from the second node to the last node. So all the differential equations from the second node to the last node, I have to solve. Okay. And we have everything. Everything is set. Uh, this is 100, and is this is we don't know this. We can remove. We have to find out tn plus 1. 0 to 10, yeah. And we have here also we have 10 intervals. And we have to write n here, function will. So now let's solve this. So there is some error, which is 40, 45. Index must not exceed. Okay. So yeah, this has to go from 2 to n plus 1. 2 to n plus 1. Now everything will be fine. Okay. Now again we have some problem. Index must not exceed 926. Uh, right. Ah, so this is n plus 1. So we have to go from here to here. How is that? Again, some other different number of elements. Oh, okay. Yeah. So here again. It's fine. It's fine. Ah, so this is length of y itself, and yeah, uh, we have got the solution. Here was slight mistake. We will see. So this is our solution, and at t is equals to 0, 0 t is equals to 0.2. So this is a 0.2. So my value is 80.3955. At 0.4, this is 0.3, this is 0.4. At t is equals to 2 seconds. 58.9745. This is 42.588. This is yeah 33.30. We'll see. There is some error. Don't know what it is. What we have done is correct. I don't know why this all our answers wrong. Yeah, zero temperature measure, and we plot it also. We are getting good thing. Plot it for let's say 20 seconds. So all the parameters are also right. There is some error here because this should not go beyond 100. I don't know why it is going. Okay. Mm. Do you guys have any questions? I think this what we have done is correct itself. I don't know why this question itself is a bit. Anyone has any questions? Uh, Asir, are you there? Hello. Okay. Okay, I think uh, we are done for today. Uh, we have solved these two practice problems. I think the answers are wrong, which are given here. So this is the method, like method of lines is what we have used for solving parabolic PD and also a hyperbolic PD in first order. So like this is how we can solve PDs, like using the method of lines. And there are also other methods like some complex methods like finite element method, finite volume method, finite difference method. So all these different kinds of methods which we can use to solve our partial differential equations. So like we have to like here we are just discretizing the uh, uh, space domain, like the spatial domain using the central difference scheme. We are approximating this second order derivative, and then we are getting some uh, like some n or n plus one, depending upon the problem, n or n plus one ordinary differential equations. So solving all the ordinary differential equations simultaneously will give us the solution to our partial differential equation, which is the numerical solution. So numerical solutions are all like always approximate, and we have to be very careful while we do our process. So whatever we are doing, so we should be very careful. Like for first order PD, we should not take the central difference technique, like because it will cause some kind of error. So and if we have norm on boundary condition, we can play with that and you like remove this host point like and substitute it with some other point depending upon the situation. So like everything can be done and uh, we can get this in a very simple and felt way. Okay. So just just try that one. We are getting what we were supposed to do. Yeah, I think what we got are the right answers, and this code has some like this. The answers in this assignment are not correct, so please don't believe it. Like whatever we have solved is correct, and we don't have any like there is no discrepancy in this. So the method which we followed in the class and we have solved is correct, and all are right solution. And these what we have given here are not correct. As long as we follow the right method and code, like, there shouldn't be any mistakes should be happening. So there are no mistakes which happen, and we did like whatever we could, and like, we got the solutions. Yeah. Okay. Today, uh, do you have guys like do you have any questions, guys? Shipra or Nasir? Like, I don't know if you are there.
Sir, I have one question, sir. Sir, if
Yeah.
software is there, the like
Mm.
Cosmol, etc. Sir, why do
Mm.
we need to read numerical things?
Like, why do we need a console and
Hmm.
all to do
No,
it,
no.
right?
When software is nowadays developed already, then why do we need to read these numerical things?
You were asking why do we need to do, like, why do we need to write the code? Like, you were
Yes,
asking
sir.
that question. So the thing is, like, software is a good thing, like, but software won't solve all the problems. Like, software will solve simple problems, but if you are like solving, like, let's say you are doing research and you are solving some complex problem, software will not have, sometimes it might not have some those capabilities to solve a problem. Then you have to modify the code. Like, in software also you can, like in Abacus, you can write your own code and run. So I think also in console you can write your own code and you can run. So sometimes softwares won't have all the capabilities, and it is like, let's say if you are like doing some kind of let's say you are doing some kind of function, and you want to serve food to the people who are coming to who are coming to the function. Like, you can just tell to a caterer, okay, these are the items which I want, and this is the amount of items. Uh, like, these are the number of people who are coming, and like you can just order them, and they will just come with all the things which you have ordered, and they will just serve. But sometimes if you don't give some proper specifications, like if you have not told a particular thing that which, like, this happens, right? Like, when we do these things, like,
Okay.
sometimes we might miss something, so
Okay, sir.
things will get messed up. So instead of like that, if you are like making your own food to serve the, like, making your own food on your own, like, you will have entire control on it, and
Hmm.
you can be very careful, and you can solve the problem. So you can think of it like this: like, when you write code, you will have the entire control on your problem. So
Oh, okay, sir.
other, yeah, especially when you solve research problems, this is the thing. And also, like, when you, even if you use software, you should know how the software is working. That is what we should be like just because you have a calculator, it doesn't mean like you should not know how to do multiplication, addition, and subtraction, right? You should use
Hmm.
calculator, like, it will save your time, but you should know how addition is going on, multiplication is going on, subtraction is going on. So that's why we are learning it. Like, even though software does everything, we should know how it is doing it, right? That's the
And sir, one more question, sir. There
yeah.
are two methods. Till now, we read one method of lines, and
Hmm.
other is discretization procedure to solve the PD.
Yeah, yeah.
Then,
Uh,
sir, when one should go with method of lines, and or is when one or use the discretization procedure.
Here, like, here in both the methods, like in method of lines, we are doing discretization in every method of lines is like we are discretizing it. So everywhere we are discretizing the domain, like Z, like with respect to Z, like whatever there is, like whatever the differential terms, like dou square t by dou Z square or dou t by dou Z, if something is there, we are discretizing it. So method, like in both, like we have solved two problems here, like one is parabolic PD and one is hyperbolic PD. In both the cases we are using method of lines.
Sir, one method of lines and another is discretization. Nth for partial differential equation. Putting the nth level, we are
uh,
getting n plus one level.
like you were talking about the first order PD or
Second order PD.
second order PD. In these lectures we have only solved using method of lines. Like you can see this problem also we have
Yes,
solved
sir.
using method of lines. This also we have used solving, like used method of lines.
Mm,
And this problem, the earlier problem, this also we have solved using the method of lines, like the bar rod problem, conduction problem.
mm. Sir, after that, the one video is there with
Okay,
there.
okay. Okay, okay. The bonus lecture, right?
Yes, sir.
Okay, okay, okay. I think, yeah, where is it? Yeah, this one, elliptic PDE. Solution for elliptic PDE. This one, right?
Yes, sir.
Yeah. So this we are not like this is like there is no time derivative here. These are both space derivatives, right?
Hmm.
So like here, just we are we should just use this discretization and we can solve it. So we don't need to solve n parts when we don't need to convert this ODE into PDE and like sorry PDE into ODE and then solve the PD ODEs again using OD45. We can this just discretize it and use the boundary conditions and solve it.
Hmm.
So if you discretize it, like you will get some set of linear algebraic equations
Hmm.
and you have to solve that system of linear algebraic equations like you can get a matrix, so you can get a matrix some k matrix into t matrix is equals to something you will get, and like if you want t, then you just invert like send k this to this side, k inverse x something. If you do, you will get the t matrix. So that's how you can get the solution.
Sir, then when should one use that
Hmm.
first type
Hmm.
and the second type?
uh, like if you have this time dependent equations like if you have t like something like this, then you
Hmm.
go for method of lines. If you don't have anything, then like if you there is no time dependence here, like t
Sir,
is not here, right? Yeah.
sir, in my portal, two bonus lectures are there
Hmm.
for finite differences for solving transient PDEs,
Yeah. Yeah.
and another is elliptic. So, sir, finite differences for solving transient PDEs,
Hmm.
they used
they have
FTCS.
used they have used which
Yes,
method?
sir. Yes, sir.
This
Forward
lecture,
in
right?
Sir,
time, central in space.
yes,
Hmm.
sir.
Why central in space? Because
Hmm.
What has been used? The forward in time and central in space, right? Yeah.
Yes, sir.
Yeah, this is also kind of similar to method of lines, but see this na in like here we were doing here in the code which we solved, we just
Hmm.
we didn't discretize with respect to time. We just used OD45 and we solved the OD.
Okay, sir.
So like if you discretize like this, like a time domain also, if you are discretizing like this,
Hmm.
like then also you can solve it, but it becomes more complicated. Like
Hmm.
instead of that, we are here we are using OD45. OD45 solves this problem. So the discretization in time is taken care of by OD45. Like you can do whatever you want. You can discretize it like this and solve it,
Hmm.
or like you can just do central in space and use the OD45 solver and do. So
Hmm.
this is like manually solving it. Like
Hmm.
here I am just like whatever the codes which we have discussed here, we have discretized only with respect to space, and time domain we have told OD45 to solve.
Hmm. Hmm.
In this lecture, like professor is telling to discretize also the time domain.
Hmm.
So this also you can do, but like this again will become very much like lengthy. Like you have to solve manually everything. So
Hmm.
instead of that, like you can give to OD45. OD45 will take care of this time domain and it will solve it.
Okay, sir.
Yeah. Whatever, like both are correct. Like you can do whatever you want, but this is a manual way of doing it.
Okay, sir. Thank you, sir.
Yeah. Where are you doing your PhD? Uh,
IIP Vishakhapatnam.
Vishakhapatnam. Okay. In what is the field of your research? Uh,
Differential equation.
oh, you are in mathematics department.
Yes, yes, sir.
Okay. Okay. Like you have done masters also in mathematics.
Yes, sir. Mathematics and
Okay. You are
computing.
from Andhra itself, or
No, no, not on the West Bengal.
okay. 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 I think if you don't have any other questions, we can stop it here for today.
Okay,
We'll
sir.
meet in the next week. Okay.
Mm. Thank you,
Okay.
sir.
Okay. Thank you guys for joining. Nasir, you have any
Yes,
question?
sir. Audible,
Yeah.
sir?
Yeah. Yeah. Nasir, you can ask.
Just to query,
Hmm.
um, uh, uh, for the research work, in case some doubt
Hmm.
is there, etc., and to have some feedback, etc. Can you suggest coming to in your among your colleagues, anyone from math department or fluid dynamics,
Uh,
we can relate in case if you have doubt in future, etc. Like that, if there anything, because I can witness the knowledge. For example, the way you have explained, etc. It is
uh,
really the even if I remember Rangakuta method, also the way in detail given, it's very clear that the amount of knowledge which you all have, it's tremendous.
hmm.
So you can always think of asking the doubt. So you anyway you have given an email ID. So, but can you
uh,
suggest any of your colleagues who are from math department or fluid
uh,
dynamics, where in case we have doubt, we can email them and we can get some feedback, and so that we can improve our knowledge also as such.
uh, like, I don't have any friends in, like all my friends, basically I have a very small circle. And whoever I have, all like everybody is like from my solid mechanics or mechanical domain. Nobody is like, I don't have any friends from fluid mechanics or mathematics. Mathematics, like people are very less here. So, uh, like, like in case if you have any doubt, like you can mail me.
Sure.
I will try to contact someone. I can like if someone if I ask someone, like they will definitely help me. But maybe if I know someone, I could have given you email. Uh, otherwise, like otherwise, if I give without uh, me knowing someone, then like they will think, okay, this guy is spamming and all.
Okay.
So
Yeah.
so like
Okay.
you can definitely mail me. You can mail me, or if like you can also take my number if you want. Then like if you ask, like I will just I have like we have many groups, WhatsApp groups. Like a lot of people are there. So like somebody will help you out. Like we just like if we ask like somebody who has some expertise will help. Like then we can like depending upon the problem, I can uh, I can give you some contact, then you can ask him or her, like they will help you out. So that's not a
Okay.
problem.
Okay, sir. Thank you. Thank you very
Because
much.
also like people have different areas of expertise. Somebody doing CFD might not be like very familiar with the experimental things or something. So like the research is very domain specific and like very specific. So depending upon the problem, you depending upon your problem, like you can find different experts. So
Yes, sir. Thank you, sir. Thank you very much.
okay, okay. You please email me. Like I'll definitely help you out. Like I'll ask
Oh,
maybe. Yeah,
so sir, almost 40, with exam whatever, then again I can start with the research work. Then in case if I have, surely I will mail you, sir. Thank
yeah,
you.
yeah. Sure. Yeah, sure. Yeah, definitely. Okay. Thank you guys for joining. You guys are joining consistently, and like that's why otherwise like there are some courses people who like uh, won't join. Like we have to just speak to the computer. So it's better to speak to some one or two people than speaking to the computer. So I am very grateful that you are joining regularly. Okay.
Sir,
Hope
one
you.
more question. Sir, while
Yeah.
doing research, how do
Hmm.
you do means, you do coding, means reproduce the paper and simultaneously read the literature, or
Hmm.
sir, or at a stage complete one paper, after that go to another paper for literature review. How do what is your approach?
Ah, yeah, that, like what you have said, s- like things are like depending upon the lab which you are in, like depending upon the faculty which you are who are like who is the faculty which